In this lesson, we will refactor our code to add single-player mode. We will implement a simple computer opponent to take over as player 2. The existing 2-player mode is still valid, so we will allow the player to choose single or 2-player mode at the start of the game. Also in this refactoring, we will leverage unit testing to help us improve the confidence that our code is correct. If we want to take turns between the player and the computer, we need to more formalize the turn concept so that it can be reliably manipulated in code. Currently, the turn concept is subtly implemented in the tabletop scene code in the onPlayerPlacedGamePieceOnBoard function. After the player places a piece, if there's not a win or a tie, we use the GamePieceHolder class to initialize the next turn. So to get started with the turn-based code, let's just refactor the tabletop with the code we would like to see that would support a computer opponent. We can then implement the missing functionality of the computer component class we're referencing here. First, stub in the computer opponent and set it to null. Then add the logic for when the computer opponent is not null, in the case when we are in single-player mode. Now let's refactor a bit to get rid of some of the code duplication and improve the readability. Extract the repeated check for victor and tie into its own function, and we'll call this isFinishedResult. Now, since the computer opponent variable is set to null here, we're essentially hard coding to the 2-player mode, which we've always been in, and all our added code should not execute. We can run through a round of the game, though, to make sure it still functions as it did previously. Now we're at the point where we need to implement our computer opponent class. Let's start with a very simple opponent. This is one where each turn it will simply place a piece at random on any available empty tile on the game board. The summary of this logic would be first from the set of unoccupied tiles, select one at random, and then place your piece on that selected tile. So of this list, we're missing the capability to fill the action expressed in number 1, getting the list of unoccupied tiles. But once we have that list, number 2 is straightforward, just selecting a random element from a list. And we already have the code to place pieces on the board that's expressed in number 3. So let's first focus on implementing this getting a list of empty tiles, and that will allow us to build the actual computer opponent class. So getting a list sounds like a responsibility of the game board. It could have a function to return a list of, say, a vector2 specifying the row and column coordinates of all empty tiles. To implement our getEmptyTiles function, let's return to unit testing and the gut framework, which we introduced in lesson 3. We'll leverage test-driven development to first write the test to add the getEmptyTiles function. Then we'll add the code to pass the test. So if we return to the test file for the game board and add the following code, when they call the fictitious getEmptyTiles function, and we just assert that we get an array back. When we run this test, as expected, we'll get a non-existent function error. So to pass the test, we add the simplest implementation of this function to the game board class. We know that it's not the correct implementation, but the goal of test-driven development is just to write enough code to pass the current failing test. We'll next write more specific tests, which will cause us to craft the correct implementation of this function. Now with this code in place, if we rerun the test, we should see them all pass. So in the next test, we'll assert that a new empty board would return all of its tiles. So in the test, again, we'll create a 2x2 board and call getEmptyTiles on it. But this time we assert that we get an array of size 4 elements back, which is the amount of elements in a 2x2 board. So now we run the test and we get this expected error because we were expecting 4 elements and we know we'd only get 0 because of the lacking implementation of this function at this time. So we return to the getEmptyTiles implementation and improve it so that it passes this current failing test. We iterate through its tile matrix, building a list of empty tiles it finds, and then finally we return that list. We now rerun the test and they should all pass. So in our next test, we assert that a partially populated board returns the expected empty tiles. We again create a 2x2 board and this time populate all but one of its tiles. And then we assert that the call to getEmptyTiles returns a single tile with the expected coordinates. We again run all the tests. In this case, they still pass, giving us confidence that our current implementation of getEmptyTiles is correct. So now if we review our summary of the turn logic for the computer opponent, we now have the capability to fulfill 1, 2, and 3. So let's start that implementation of the computer opponent class. So for the computer opponent class, there's no scene associated with it. So let's just create a new script in a entities computer opponent folder, and we'll call it computeropponent.gd. In this class, we have a single public takeTurn function and a helper private function called selectTile. The takeTurn function receives a list of empty tiles as a parameter. Of that list, it selects a tile at random and then places its game piece type, X or O, on the selected tile. So now let's get ready to test in single player mode. Return to the tabletop scene script, and we can hardcode in a computer opponent in the ready function, and this presence essentially puts us into single player mode. This will cause us to fall into the single player logic in the on-player placed game piece on board function, since computer opponent is now truthy, and if not computer opponent will not trigger. We first see if the computer opponent's game piece type has been set, and this is done because the player will always have taken the first turn, so the computer opponent's game piece is not set. If it's not set, we simply set it to that opposite of the player's type. Then we call the computer opponent's takeTurn function and pass in the game board's list of empty tiles. And then finally we check if the computer opponent's turn resulted in a win or a tie on the board. So we're almost ready to play in single player, but if we look at the game piece holder, we'll notice a problem with the initialize player turn function. Currently it assumes that we are toggling sides between player 1 and player 2. In the single player mode, in the initialize player, rather than setting up the second player's piece, we need to set up the single player's piece since there is no second player, and at this point the computer opponent has already taken their turn. As mentioned, we want to keep both two-player and single-player modes as an option. To do that, we'll introduce a Boolean to the initialize player turn function, specifying if we are in single-player or two-player mode. We will then refactor game piece holder based on the value of that Boolean. In set pieces holder state, if in single-player mode, we simply spawn a new single-player game piece and deactivate the computer's piece. Otherwise, we follow the existing two-player logic. Then as a final step, we introduce this Boolean to the activate piece function. So this function will no longer always be setting to true, so we change the name to set piece state, and then add that isActive flag as a parameter. And then finally apply the value of that parameter rather than just setting to true. Now in the tabletop code, where we call initialize player turn, we add the in single player mode Boolean value, which is true if there is a valid computer opponent object present. If we run the test, we get an error since we changed the function signature of initialize player turn, and that's not represented in the test at this point. So now we go to the test code for the game piece holder, and the existing test we can still use. We'll convert it to the two-player test. Let's just rename it, and then we'll introduce and utilize the player mode Boolean. Then we'll create a second version of this test, which will be for the single player. Again, we'll utilize the correct value of the Boolean for player mode. So with these tests in place and passing, we have a base level of confidence that initialize player turn functions correctly. You could, of course, write more tests, but we'll leave that as an additional exercise for yourself. So now since we have a computer opponent hard-coded in the tabletop class, we can play the game in single player mode. If we start the game, you'll see as soon as you place a piece on the board, the computer will place another piece at random on an unoccupied tile, and then it would be your turn again. And additionally, we can test the game in the original two-player mode by commenting out the line, which creates the computer opponent. And now in gameplay, we can see that we truly are in that original two-player mode. So we now have single and two-player modes, but of course this commenting and uncommenting of code isn't acceptable for our finished game. We'll address this in the next lesson by adding a game state storage mechanism. With that in place, at the start of the game, the player will choose single or two-player mode, and then that choice will be stored in the game state mechanism, which will make it available to any other code in the game. In addition, we'll also add an end screen where we'll also use that game state mechanism to store things such as the tally of wins for X and O, and who was the last player to win, and we'll display that on that end screen. Thanks as all for watching, and comment below if you have any questions. Likes are always appreciated. Comment and bell so you don't miss any future episodes. Thank you.